Welcome back to G Fun Facts Online. Today, we are diving deep into a technological breakthrough that is poised to redefine our relationship with robotics, energy, and the microscopic world. We often think of robots as these massive, power-hungry machines, drones that need battery swaps every 20 minutes, or factory arms wired directly into the grid. But what happens when you strip away the battery entirely? What happens when you shrink a robot down to the size of a penny, yet demand that it thinks, moves, and communicates autonomously? That is exactly what researchers at the University of Washington's Paul G. Allen School of Computer Science and Engineering have achieved. They have created the MilliMobile. This isn't just a small robot, it is a paradigm shift. It is a 10 by 10 millimeter autonomous microrobot that weighs about as much as a raisin, specifically 1.1 grams, and it runs indefinitely on nothing but ambient light and radio waves. In this episode, we are going to break down exactly how this engineering marvel works, the physics challenges of moving at the micro scale, and why this specific device might be the key to the future of the Internet of Things. Let's start with the physical reality of the MilliMobile. When you look at most microrobots developed in labs over the last decade, they usually come with a catch. They are often tethered by wires, or they require a perfectly smooth lab-grade surface to move, or they are steered by massive external magnets. The MilliMobile is different. It is built for the real world. It features a chassis made from carbon fiber, chosen for its incredible strength-to-weight ratio, and it moves using 4 wheels. That might sound standard, but at this scale, using wheels is a deliberate engineering choice. Many competitors use vibration or stick-slip motion, which works fine on glass, but fails on concrete or packed soil. By using a custom miniature drive system with electromagnetic motors and wheels, the MilliMobile can traverse rougher surfaces like carpet, concrete, and soil, carrying a payload of up to 3 times its own body weight. That payload capacity is crucial because it means this isn't just a mobile speck of dust, it's a cargo hauler for sensors. But the true genius of the MilliMobile lies in its power system. This is where we get into the core innovation known as intermittent motion. To understand why this is revolutionary, we have to look at the power budget. The ambient signals surrounding us, the light in your kitchen, or the Wi-Fi signals bouncing off the walls, contain energy. But it is trace energy. We are talking about tens of microwatts. A standard electric motor, however, needs milliwatts to turn. That is a discrepancy of thousands of times. You cannot just hook a solar panel to a motor at this scale. The motor wouldn't even budge. The UW team solved this by adapting a concept from computer science called intermittent computing. Imagine you are trying to run a marathon, but you can only hold your breath for 5 seconds at a time. You would run as hard as you can for those 5 seconds, stop, breathe, recover, and then sprint again. That is what the MilliMobile does with electricity. It sits perfectly still, harvesting those tiny microwatts from light or radio waves into an onboard capacitor. This capacitor acts like a small bucket. Once the bucket is full, which might take a split second or a few seconds depending on the light, the robot releases that energy in a high-power burst. This pulse spins the motors for a tiny fraction of a second, moving the robot a fraction of a millimeter. Then, it immediately goes back to sleep, to recharge. By breaking continuous motion into thousands of discrete microsteps, the robot mimics the movement of an inchworm. It moves incrementally, but because it's doing this autonomously, it can keep moving indefinitely. It effectively divorces the concept of autonomy from the limitations of a battery lifespan. Now, let's discuss where this energy comes from. The MilliMobile is what we call poly-powered. It is a scavenger. It is equipped with tiny solar cells, or photodiodes, that are incredibly efficient. In direct sunlight, the harvesting is rapid, allowing the robot to move at speeds up to 5.5 millimeters per second, which is roughly 30 feet per hour. That sounds slow to a human, but for a device this small, it is significant. More impressively, it can operate in standard indoor lighting or even low-light conditions. But what if it crawls under a couch or into a dark pipe? That is where the radio frequency, or RF, harvesting comes in. It can pull energy from Wi-Fi routers or dedicated transmitters, operating with signals as weak as -10 decibel milliwatts. This ensures that the robot doesn't just die when the lights go out, it simply switches its food source. What truly sets the MilliMobile apart from other microrobots is its brain. Most robots this size are dumb terminals controlled by a human with a joystick. The MilliMobile steers itself. It carries a microcontroller that has been optimized to handle those constant power failures we mentioned earlier. Every time it pulses and sleeps, the brain has to remember what it was doing. It uses onboard light sensors to perform phototaxis, meaning it can detect the direction of the strongest light source and steer toward it using tank-style steering. This allows the robot to self-optimize. It hunts for energy so it can recharge faster. It also transmits data. In tests, despite having no battery, it successfully beamed sensor data over Bluetooth across a distance of 200 meters, or 650 feet. That is a staggering range for a device powered by harvested background noise. Let's pivot to the physics challenges, because scaling down introduces problems that don't exist for human-sized robots. The biggest enemy at this scale is friction versus inertia. If you drive a car and take your foot off the gas, the car keeps rolling because of its mass and inertia. At the gram scale, mass is so low that inertia is negligible. Surface forces like friction and electrostatic adhesion dominate everything. When the MilliMobile's motor stops, the robot stops instantly. It doesn't coast. This means the drive system had to be engineered to overcome high static friction with every single step, essentially jump-starting itself thousands of times an hour. Furthermore, there is the power-to-weight paradox. Usually, tiny batteries and motors are less efficient than big ones. By removing the battery entirely, the researchers sidestepped the weight issue, creating a device that is theoretically immortal in terms of runtime. So what do we do with a swarm of immortal, penny-sized robots? The applications are fascinating. The researchers envision these devices in Industrial IoT. Imagine a chemical plant with miles of complex piping. Installing fixed sensors on every meter of pipe is too expensive. But you could release a swarm of MilliMobiles. They could crawl along the pipes, scavenging energy from the facility's lighting, using gas sensors to sniff for leaks, or thermal sensors to check for overheating. If they find an anomaly, they broadcast the location. Because they are so small, they can fit into tight spaces where humans or drones simply cannot go. Another massive application is smart agriculture. Precision farming relies on data, specifically soil moisture and humidity. Instead of planting expensive static sensor stations that require batteries, which eventually leak chemicals into the soil, a farmer could scatter hundreds of MilliMobiles across a field. They would move slowly, powered by the sun, sampling soil conditions at different locations to create a high-resolution heat map of the field's health. And let's not overlook infrastructure monitoring. Concrete bridges and buildings develop microcracks over decades. MilliMobiles could be deployed into crawl spaces, or even embedded within the structures during construction, waking up only occasionally to check for vibrations or structural integrity, essentially giving the building a nervous system. When we compare this to existing technology, the MilliMobile fills a unique gap. Traditional robots have autonomy, but limited battery life. Insect cyborgs, yes, those exist, are hard to control and have biological lifespans. Magnetic microrobots have unlimited life, but are tethered to the range of the magnetic coil controlling them. The MilliMobile is the only one that offers indefinite lifespan, full autonomy, and untethered range in a package this small. Looking to the future, the University of Washington team views this strictly as a primitive building block. The goal is swarm intelligence. Future iterations will likely feature peer-to-peer communication, allowing robots to talk to one another. If one robot finds a crack in a bridge, it could summon others to verify it. There is also the integration with 6G networks. As 6G rolls out with integrated backscatter and energy beaming capabilities, MilliMobiles could become a standard part of our urban infrastructure, harvesting energy directly from cellular towers to monitor our cities. In conclusion, the development of the MilliMobile proves that with clever engineering, we don't need massive power plants to create intelligent motion. By listening to the quiet energy already buzzing around us, in the form of light and radio waves, we can animate the inanimate. We are moving from an era of energy storage to an era of energy harvesting, and that shift is going to populate our world with tiny, helpful, autonomous machines. That's it for today's deep dive into the MilliMobile. Thanks for listening to G Fun Facts Online.